So let's look at optimization in many dimensions. So what we're trying to find is the minimum, is to minimize f of p with respect to p, where p belongs now in Rm, right? So p could be a vector like this, p1 till pm, where each of them is a real number. F, of course, is a real number, right? So when you're trying to minimize a function, it's one number typically. You can either say we are trying to minimize the function f of p, or trying to find the minimum value of f of p, or trying to find the point at which the function has minimized p star. Okay, and let's say for the moment that there are no other constraints on p. Okay, just like before. So what are the necessary and sufficient conditions now for optimality? This is something that we have seen before briefly. Necessary condition for an interior minimum, not at infinity, right, is just like before, the slope needs to be equal to 0, but because we are now in m dimensions, the slope in every single direction in that m dimensional space has to be 0 at the point, well, p star here, right? This is p here, and at that point p star, the slope needs to be equal to 0 in every direction. What that means functionally is that you take the partial derivative of f with respect to p1, p2, p3, etc., and evaluate it at your p star, and all those partial derivatives are going to be equal to 0. If all the partial derivatives are equal to 0, then the partial derivatives are basically slopes in each of the m directions. If those slopes in those m directions are equal to 0, then the slope in any other new direction can be represented as a linear combination of those m slopes, and the slope in any other direction will also be equal to 0. Okay, so that's the necessary condition: slope equal to 0, but just generalized to m dimensions. The idea is that if all the slopes were not 0, then we can follow the non-zero slope to find a neighboring point that has a lower f value. Okay, so if the slope is not equal to 0, then that means that you can go down the slope and find a lower f value, and which means that you have to have slope equal to 0 if you're claiming something as a minimum. Okay? All the slopes equal to 0, or all the partial derivative equal to 0, is mathematically the same as saying the gradient represented by the symbol with respect to p, which sometimes people might represent in this manner. If it's clear what quantity you're taking the gradient with respect to, just use this. But if it's not clear, if there are multiple options, we might use this. The gradient is just all the partial derivatives strung together into an array, and they need to be equal to 0, right? And that's the necessary condition for a local minimum. Local minimum. As usual, the slope equal to 0 condition can be true at a minimum, maximum, saddle points, right? They're not true just at a minimum. At a minimum, you need to have this to be true, but there may also be other points that may satisfy this condition. Okay, so to decide between the choices, just like before, we need to look at the second derivative, which tell us something about the local curvature of the function. Now, how do we think about second derivatives in m dimensions? Just recall, if you have Taylor series in one dimension, then your f of p equals, if you're expanding a Taylor series about p naught, then f of p equals f of p naught plus p minus p naught times first derivative plus half p minus p naught square second derivative. This is if p and p and r are one dimensional, right? Just in R. And then we have some higher order terms. So this is the second order term, and an expression like this would be considered a quadratic approximation of f of p around p equal to p naught. Okay, so that's in 1D. What does the m dimensional version look like? So if you take a function in m dimensions, like where p is belonging to Rm, then f of p scalar equals f of p naught, another scalar, plus gradient transpose p minus p naught plus half p minus p naught transpose h p minus p naught plus higher order terms. So this is the multidimensional Taylor series. Okay. Again, the g is the gradient. We just wrote it as g because it's a bit cumbersome to write grad f transpose there. This is going to be an m by 1 matrix. H, this function h. So recall that p, p naught are all m by 1 matrices, right? This matrix H is actually an m by m matrix of all possible second partial derivatives, right? So d square f by dp1 square, d square f by dp1 dp2, d square f by dp2 dp1, etc. Right? So it's a matrix of second partial derivatives. It's called the Hessian matrix. The general element is basically d square f by dpi dpj. So that's called the Hessian matrix. It's basically the second derivative of the function in n dimension. Now this matrix, it turns out, is always symmetric. However crazy the function is, it's always symmetric. And that's because you could change the order of differentiation, it turns out, and the order of differentiation does not affect the value of the derivative for higher derivatives. This is in fact what we mean by twice continuously differentiable. The order of the derivatives not mattering is one of the conditions, I guess, implicitly. Okay, so that's the Hessian matrix, that's the second derivative. What we were looking at was a condition, just like saying second derivative greater than 0 for minimum in 1D. What is the corresponding condition on the Hessian matrix? And it turns out the corresponding condition, specifically the sufficient condition for local minimum in m dimensions, is the first gradient needs to be equal to 0 and all the eigenvalues of H, this matrix, needs to be greater than 0, right? So it turns out you want the eigenvalues of H to be greater than 0. H that satisfy this condition are called symmetric positive definite matrices. If all your eigenvalues are negative, then they are called negative definite matrices. If some eigenvalues are positive and some negative and maybe some 0, then the matrix would be called indefinite. For a minimum, we want it to be positive definite. Okay. These are called, like I said, symmetric positive definite, but what we want is positive definiteness. Symmetric just happens. Okay, so let's look at some examples just to build some intuition for Hessians and gradients and things like that. Let's take a very simple function of two variables, this whole thing. We can find the gradient, just do the partial derivatives, that's the gradient. You differentiate once more to get the Hessians, the 2 by 2 matrix. Clearly it's symmetric, and we can find eigenvalues if we want. Okay. For a quadratic function, this is a quadratic function, two variables. The Hessian is a constant. It's a constant. The gradient itself is not a constant. The gradient depends on x and y. But the Hessian is a constant, and that's because it is a quadratic function. If you have a more nonlinear function, the Hessian will not be a constant, the gradient will not be a constant, etc. Okay. Okay. So let's see a few more examples. If you have a function that's a function of p1 and p2, which is just constant plus linear function of p1 and p2, then, well, I guess that's what that looks like in general. If you have a function that looks like this, where lambda 1 p1 square plus lambda 2 p1 square lambda 1 and lambda 2 are greater than 0, then we can sort of quickly check that at the origin of P1, P2, the gradient equal to 0, first of all, and the Hessian is, so it's a potential minimum. And just by looking at this function, you can sort of say that that's the minimum because 0 is the lowest value that this function can take. In any case, the Hessian has this diagonal form. We can just twice differentiate this function to get that. And if the eigenvalues are going to be 2 lambda 1 and 2 lambda 2, which are going to be greater than 0 if lambda 1 and lambda 2 are greater than 0. If you actually plot this function of two variables, it's going to look like this ball. And lambda 1 and lambda 2 are actually 2 lambda 1 and 2 lambda 2 are actually going to be the curvatures of this function along P1 and P2. Okay. Sort of a useful concept in doing optimization is this notion of a level set. So visualizing a function, you can represent the function as a function of two variables like this. Sometimes it's more convenient to represent it like this, which is saying take this picture and then slice it at different levels of the function value, and the set of all p-values that correspond to a particular f value is called a level set, right? Level. If you've seen topographical maps which provide contours for uneven terrain, for instance, or mountains and valleys and so on, those are basically level sets of the height of that point, right? In any case, so it turns out that the level sets for a function like this will actually be ellipses in general. If we have the exact sort of reverse negative function where f is minus lambda 1 p1 square minus lambda 2 p2 square with lambda 1 and lambda 2 greater than 0, it's actually a maximum at the origin, and the Hessian is this quantity, and if lambda 1 and lambda 2 are greater than 0, of course, the eigenvalues, which in this case are the diagonal values, are going to be negative. Okay. And then finally, so we've seen that gradient equal to 0 does not mean minimum. It can be minimum or maximum. We've already seen those two things. Finally, we also have the possibility that it's something else, right? Specifically, if you say lambda 1 and lambda 2 are greater than 0, the function is something like lambda 1 p1 square minus lambda 2 p2 square. At the origin, again, the gradient is equal to 0, so it could be a minimum, could be a maximum, could be something else. And this is actually the something else, where the Hessian has 2 lambda 1 and minus 2 lambda 2 on the diagonal, and those are going to be the eigenvalues. If you just take a look at this function, is this a minimum or a maximum? So if you forget P2 exists, just set P2 equal to 0, and just look at f equals lambda 1 p1 square, that function is going to look like this, lambda 1 p1 square. Okay. Then so f as a function of p1 has a minimum at the origin. If you just ignore p1 and look at p2, f equals minus lambda 2 p2 square, f as a function of p2 looks like this, where it has a maximum at p2 equals 0, right? So this function is kind of a minimum along one direction, maximum along another direction. And this can happen in m dimensions as well, where there are a few directions in which the function seems like a minimum and a few directions in which the function seems like a maximum. And of course it's neither. So a function might look like this, right? So a function that has literally this property will look like this, where p1, p2 along p2, maybe I mislabeled it, but doesn't matter. In this case, along P2, it's a minimum, and P1 it's a maximum. I should just interchange P1 and P2 here. Okay. The next video is going to be about methods for solving these optimization problems.